Well, in this section of the torque on a system of particles, we have learned three different concepts. The concept number one is if a system has two or more than two particles, and they are acted upon by external forces, so also the internal forces, sum of torque produced by the internal forces, that is called internal torque, is equal to 0. This is number one concept. Previously you learned that the sum of all internal forces will always be equal to 0, because the internal forces, they appear in the form of action reaction pair. They are equal, opposite and collinear. As per Newton's third law, sum of all internal forces happening as action reaction pair, action reaction pair, if this is plus F, this is minus F. The net force will be 0. Newton's third law. The second concept is the net torque about any point is the summation of the torque produced by the external forces and that produced by the internal forces. Since the internal torque is 0, the torque produced by the internal force is 0. The net torque is equal to the sum of torque produced by the external forces only. The third idea we are getting, in the system of particle, we have the center of mass. Let it be C. So the third point is the torque of the external forces about any fixed point is equal to torque of all forces, all external forces about the center of mass, that is tau c. The internal forces cannot produce a torque about any point. It may be center of mass, it may be any other point, plus torque of the net force, that is equal to sum of all external forces supposed to be acting at the center of mass about the given point. RC is the position vector of the center of mass with respect to the reference point cross the net force. Under these three ideas, let us solve some problems. Let us take a system of two particles. On this particle 1, force F is acting, and particle 2, force 2F is acting. Distance of separation between these two particles or 2 points, let be L. This particle has mass m, this particle also has mass m. Take the reference point here somewhere. On the line of separation or line connecting these two particles, this distance is L. This is the center of mass. Center of mass is at a distance of L by 2 from both particles. So we have to verify the formula. Tau O is equal to tau C plus RC cross F net. Tau O is equal to net force experienced by the system. Tau is equal to the net torque experienced by the system about the given point. That's equal to this force F will produce the torque in which sense? Clockwise sense. That's equal to L into F minus KK. And torque produced by this force 2F. Here this force 2F act up. The question is, verify the formula. Tau O is equal to tau C plus RC cross net force. The net force acting on the system is equal to 2F plus minus F. So net force is equal to 2F minus F, that is F up or Jacob. This net force will produce a torque about the given point in anticlockwise sense. So tau O is equal to torque due to this force about this point plus torque due to this force about this point. This force will produce a torque in a clockwise sense about this point minus L into F KK. This force will produce a torque about this point in anticlockwise sense, and R vector for this force is L plus L 2L. So 2L into F KK. The net force, the net torque about this point will be equal to L F KK in anticlockwise sense. Well, this is left hand side. Right hand side is tau C plus RC cross F net. This tau C is the torque you are measuring sitting with the center of mass frame. With respect to center of mass, this force will produce a torque in this way. Anticlockwise sense, this force will produce a torque in anticlockwise sense. Therefore, torque produced by F is L into F KK. Torque produced by 2F above the center of mass is equal to L into 2F, that is 2LF KK. That's equal to 3LF KK. This is tau C. Now RC cross F net. These two forces will produce a net force, that is F Jacob, supposed to be acting at the center of mass. Therefore, you should remove these two forces to have the net translatory effect, or remove these two forces and place the resultant at the center of mass. And this resultant force will produce a torque. How much? This is L by 2, this is L. So this distance is 3L by 2. So this resultant force supposed to be acting at the center of mass will produce a torque about this point O. That is RC cross F net. F into 3L by 2 in anticlockwise sense. KAB. Now, you have to add this to then the right hand side term will be equal to tau C plus RC cross F net. What is tau C? 3LF KAB plus RC cross F net 3 by 2 LF KAB. This will be 3 into 2 6 plus 3 9 9 by 2 L into F KAB. Right hand side must be equal to left hand side. The left hand side torque about this point O. One force is acting down, other force is acting up. This force is producing a torque in negative z direction, L into F. This force produces a torque at a distance of 2L from the given point. This force is 2F. Therefore, 2L into 2F. How much? 2 into 2, 4 into F KAB. So, minus 1 plus 4, 3. Well, let us reevaluate the steps. Verify the formula tau equal to tau C plus RC cross F net. Tau is equal to about this point. This force will produce a clockwise torque minus KAB into L into F, and this force produces an anti-clockwise torque. Distance is 2L, the angle is 90 degrees, sine 91, so 2L into 2F KAB. That's equal to 2 into 2 minus 1, that's 3 LF KAB. Absolutely correct. Right hand side term tau C plus RC cross F net. Tau C is the torque of these two forces taken with respect to the center of mass. Torque of this force about the center of mass is this force is producing a turning effect in positive z direction or anticlockwise direction. This distance is L. The distance between the force and the center of mass is not L, this is L by 2. That is the mistake. So when you recheck, you can understand the mistake. Well, into F in anticlockwise direction, and here the force is acting and this distance is L by 2 and the force is 2F. So you are getting in which direction? Anticlockwise direction. Getting cancelled, the two will be getting cancelled in numerator and denominator. So you are getting LF by 2, that is 3 by 2 LF in KAB direction. Now come to the second part, RC cross F net. What is the net force? Minus F plus 2F will be equal to F, supposed to be acting at the center of mass. Therefore, you eliminate these two forces and place its resultant at its center of mass. This force is F, 2F minus 2F minus F, or 2F JKAB plus minus F JKAB, that's equal to F JKAB in upward direction. This force supposed to be acting at the center of mass will produce a torque in which sense? About this point. This is the RC equal to 3L by 2 and this is 90 degree. So 3L by 2 into F, that will be equal to 3L by 2 F K cap. So if you add this two, how much you are getting? 3 by 2 L F K cap plus 3 by 2 L F K cap will be equal to 3 L F K cap, and this is equal to the left hand side. Hence, we have verified the formula. This is a great formula which states that the torque experienced by a system of particles about any fixed point is equal to torque experienced by the same system of particles about the center of mass plus the torque of the net force supposed to be acting at the center of mass taken with respect to that given point. For the sake of simplicity, that point should be stationary or it may move with constant velocity. Then only you can say that that point is an inertial point, an inertial reference frame. That's very interesting concept. Using this concept, we can proceed to find the angular momentum of a system of particles. Before that, I would like to take a system of two particles, 1 and 2. Here the force F is acting, here the force minus F is acting. Two equal and opposite forces. And you take a reference point. Here this is R1, position vector. Here the position vector is R2. We have to calculate torque about O, torque about C, find torque about any outside reference point and torque about the center of mass point. So in this problem, system of two particles and two forces are acting. Now, take their masses m and 2m. Find the torque of these two forces about this point. Tau O is equal to torque produced by this force F, that is R1 cross F, plus torque produced by this force minus F, that is R2 cross minus F vector, is equal to R1 minus R2 cross F vector. Let it be, this vector be, suppose R. A triangle of vector addition, R2 plus R is equal to R1. So R is equal to R1 minus R2. So R1 minus R2 can be written as R. So tau is equal to R cross F. So it doesn't depend upon any reference point which does not depend upon any reference point or reference frame. If this is so, torque about the center of mass must be this much. Tau C is equal to R1C cross F. Torque produced by this force with respect to center of mass frame, and torque produced by the opposite force with respect to the center of mass frame. The position vector is R2C plus R2C cross minus F. So you are getting R1C vector minus R2C vector cross F. But this vector itself, this is R1C and this is R2C. R1C minus R2C. This is minus R2C. R1C plus minus R2C is nothing but R vector again. So this is again R vector. So in this way you can prove that when two equal and opposite forces are acting on a system, the net torque experienced by the system due to these two equal and opposite forces does not depend upon any reference frame, and that type of torque produced by a couple of forces is called couple. Torque produced by two equal and opposite forces is called couple, and the couple does not depend upon any reference point. It is a constant quantity, and as a corollary, if these forces F and minus F are collinear, they are equal and opposite, but in this case they are not collinear. If they are collinear, then we can call these forces action reaction pair if the particles interact for any interaction. Even though the particles do not interact, they may experience equal and opposite force. In that case also we can call these two forces collinear when they are equal in magnitude, oppositely directed, and they pass or act along the same line. If these forces are collinear, then F and minus F, particle 1, particle 2, and this vector R cross F will be equal to 0. Then the torque produced by these two forces is always 0. It may be internal forces, a pair of internal forces, or it may be two forces acting on these 2 points of the system. May be the external forces if they are equal in magnitude, oppositely directed, and collinear. Then the net force will be always, net torque is always equal to 0. Needless to mention, the net force is 0 always. So this is a great lesson. We learned that whenever a system experiences an internal force, the net torque of the internal forces is 0, because the internal forces, they happen as action-reaction pairs. For a pair of action-reaction force, the net torque is 0, and the net action-reaction pairs, or the net internal force, is always equal to 0. However, if the forces are acting from outside on these points, on the particles and these forces are equal and opposite and collinear, then in that case also the net force is 0 and net torque is 0 for all the points of the universe. It doesn't depend upon the reference point. So in general, a couple is a torque produced by two equal and opposite forces. You can take the center of mass as a point, or you can take any point in the universe. About all these points, the torque produced by equal and opposite forces remains the same for all the points. Therefore, the couple does not depend upon any reference frame. We will encounter the problems of the couple in electricity as the force experienced by an electric dipole, and in magnetics the force experienced by a magnetic dipole or a magnet when placed in an external electric and magnetic field. There we will use the same concept. We should not ask about which point, about any point, about the center of mass point, about any point in the universe. The net torque remains the same.